Well, hello everyone. Welcome to part 4 into my coding example of DLL injection into all processes. And today we'll continue coding our Windows driver, and today I will try to start writing code to create a section. So let's go back to our coding platform. Let's start Visual Studio and see where we left off. If you remember, our project is called Inject All. So let's open it up. And let's quickly review. So what we did, we wrote some basic scaffolding to start our driver, to set up our callback routine for when all the modules, for when any module in any user mode process is loaded. By the way, not just user mode, into any process is mapped. And then we can also unload it here in free resources. That's the function that unloads it. And then we have our callback, where we created a filter where we are looking for where we're skipping system images, which we don't need. We make sure that the process came from the process that we want. We make sure that the name of the module is actually kernel 32 DLL, and I explained why in the previous installment. Then we also made sure that the request came from load DLL, which is an internal NT version of load library, so this is important. And then we also put a little filter here. We limited our process to just Notepad, and this is done only for debugging purposes, so that we don't mess up the whole system. In this case, we'll just experiment with Notepad. Okay, so then if this filter passes, and we basically skip any other module, we don't need it, and then we just output little debugging information with the name of the image, with the process ID, and also whether or not the process that we're currently in is a WOW64, which is a 32-bit process running in a 64-bit OS. And this was pretty much where we left off. So at this point, we need to start creating our section. And section, if you remember, again, I'm going to bring you back to this ugly diagram. Section is the same as the module or a DLL, so it's kind of like kernel way of calling shared chunk of memory. They call it section. Okay, so at this point I am thinking that I will create a separate class to do that, because I'm not going to put it all into C function. There's too much code. And that will be the most of our code that deals with sections. Okay, so for the lack of a better name, I'm going to call it CSection. And I'm going to say OK. And here you go. We have a little class. And let's see, and we have class, and we have our implementation here. And again, I'm going to put a comment here, and I'm going to say class that deals with mapping of a section or DLL, not DEL. Okay, so I'm going to do it here as well. And just to make sure it actually uses our driver types header, and this is custom types so that we can have access to it. Okay, and we will be putting all the code that deals with our creation of the section into this class. Yeah, so at this point we need to create a custom structure that will contain our DLL stats. Now, what is that? Well, basically all the stuff that all the kind of information about the section will be kept here. Now this is very important thing since we're going into C++ territory here. Let's make a little note here that we cannot use constructor or destructor here. Now the reason being is that when we use these things, when we use constructors and destructors and declare our structure or our class on a global scale, that invokes CRT and invokes certain internal functions that actually initialize and run our constructors. Well, we can't do this because we are in the driver. Technically, we're not supposed to be doing any C++ code, and if we do, well, we will run into an issue. So in this case, we cannot use any of destructors and constructors. So just put a little note there. Okay, so let's go into driver types, and let's see, like over here, let's define an enum and declare section type. So this will be the type of the section that we might create. Well, there are technically two types. Let's just call it section type. And I'm going to copy it like this. So one will be so-called native, and the second one will be a wow section. So let me explain real quick. So the first one is, like I said, a native section, and let's say meaning 64-bit on a 64-bit OS, or 32-bit on a 32-bit OS. So in other words, when our section or a module is matching the bitness of the operating system. In other words, it's a native section. And the second one is a wow64 section. Now this is a very bad and conflicting naming. That's why I don't use 64. Technically, the meaning is that this is a 32-bit on a 64-bit OS. So it's not really 64, it's 32-bit DLL on a 64-bit OS. Okay, so this will be, so we can have, well, we will technically have two types of sections, 32-bit and 64-bit, or native one, which is the matching bitness. Okay, so let's go back into our section header here, and what we will do, we will set up these internal parameters for our DLL. So one would be section type, and here we would say type of section. So we will define it internally. Now then we will also need section object itself that we will create. Let's just say if not null, section object for the DLL being injected. So when we load our DLL or section for it, it will go here, and then we will add additional details here as we go. Now we also need an internal method here that will tell us, that will return true if data in the struct is valid. Okay, so by default we will null it out. Again, we can't do it here in a constructor, we'll do it externally, and here we will just check. Now section type doesn't matter, but here we need to make sure that section is not null, and if so, at this point we will assume that our data is valid. Okay, so that will be that, and at this point we can start coding a section. I'm sorry, our class. Well, first of all, the class itself will also have a section type, and then it will have several public methods. Now, one that we need to do, we need to initialize it. And we initialize it with a section type. Now, because we can't have any, let's put it here as well, that we cannot use constructors and destructors, we have to initialize our section. So we kind of do the C way, and we'll do it in the initialize method. So let's add definition for it, and let's switch to it. Let's free up some space, and here's our initialize method. So we don't need that. Let's just put a quick comment. Initialize this object, and let's just do the same thing here, that we cannot call, you know, destructor and constructor, and type is type of section or DLL that this section will represent. Again, I'm just adding comments here as much as I can, so that, you know, next developer can understand what I'm doing here. And we do this, and we have to return status. Well, let's just for now return status success, so that, you know, our module can compile. Let's make sure that we actually can compile. And so far it does compile without a problem. Okay, well, the next one, now the first one doesn't do anything, but the next one, we need to, well, let's write a singleton here that will give us a section object. And I'll explain what I'm doing in a little bit. So it will be a, like I said, a singleton that we can call from outside that will create our section. It will create it only once. And then any subsequent calls, it will just return a pointer to it, and it will do so in this variable, section info. And let's add it to, in this case, let's add a declaration for it. And yeah, it will be public as well. But in this case, we will allow a null value here as default. And let's write a little description of what this function does. By the way, just noticed my awful grammar here and misspellings. Okay, so back to the function. Let's just write that it, well, we need to call it to get DLL section object, and it will create it only once if it wasn't created earlier. Well, kind of like a singleton. Now this variable, if not null, receives the section object info, or null if error, and return, well, status of operation. So that's kind of like simple, right? It's just a status code, and by default, let's just assume that we have success. You know, we'll obviously adjust it later, and we return it. Okay, so this is just a basic description of what the function does. And since we don't have our constructor, let's make sure that this method, was called. And this is just a debugging assertion check, so it will not go into production. And at this point, what we need to do, we need to see that the section type is either of two values that we specified. So it's either native, where is it? It's either native or it's a wow section. Now, if the object is not initialized, it will have some garbage in here, and this assertion will trigger, and that will tell us that we need to call initialize. Again, the reason we can't set this parameter in a constructor is because we cannot call a constructor, we cannot use them. And the reason being is that CSection will be declared on a global scale. Let's just, by the way, do that. If we go into a driver main and we scroll all the way up where our global variables are, we can also add here, and let's just call it sec for native section object. Now, the reason being is that I'm declaring it like this is because we will always have a native section. And by the way, we need to include our C section here, and let's just say section DLL specific. Okay, so that will add our section here. And also, if def win64, let's see, and if this is a preprocessor check, condition check. If we are building 64 build, we also need to include a section wow. And let's just put a comment here, wow 64 section object used only for a 64-bit build. Because again, when we are running on a 64-bit OS, we have to assume the possibility of injecting a code not only into 64-bit processes, but also into 32-bit ones. Okay, well, again, so going back to why we can't use constructor on either of these objects is because it is used on a global scale. So because of here, if it had constructor, it would actually try to put constructor code outside of all the scope into the CRT or the C runtime. Because our driver cannot have any C runtime, that would cause problems for us. So that is why we cannot use constructors. So let's compile. And okay, well, here we get to the point where we have a warning. So to make sure that we can deal with it, let's kind of like fill out the result here. And for now, I'm just going to put 0, but we will fill it in later. Okay, so at this point we can compile our scaffolding. So let's write our code. Okay, well, first thing first, we need to use the singleton approach here. And the way I would do that is by using a function. I'm going to use internal kernel API that provides singleton implementation. It's called RtlRunOnceBeginInitialize. Now, if you look, you can probably, let's see, if we go into documentation, it will tell us how this API works. So basically what happens here is that it takes a context for run once, and then it takes flags and it takes the context that we provide. So let's create that context. Let's just call it void context, it will be null by default. And in this context, we will store a reference to our DLL stats, so we can just return it here. I'll have to do explicit cast here. Okay, so by default, it will return null, which would mean an error. But for now, we get a status code, and if we look at the definition here, we get pending in case this is the first time we call this function. If status equals pending, then let's make a comment. We get here only during the first initialization. Okay, and let's fill in the rest of the possibilities here. So I usually like to kind of like fill them in from the get-go so that I don't miss anything. So we have several options here. We have status code. You know what, we'll actually just use one, because if you look at the documentation here, we can have success and pending. Now we get success if we initialized it and the second call goes through, it will fill out our context. By the way, you know what, I apologize, let's fill in here. Now we are not using any flags, so let's specify 0, and we are returning our context. And over here we need to provide RtlRunOnce. Well, it's not a context, it's the structure that contains all the information about this API. So if we receive success, it means that we had already initialized and we get pending for the first call. But in case we get something else, which is, you know, entirely possible knowing Windows APIs, we actually need to deal with an error. And I can just use our debug print line to basically output the problem. And we can say that this is an error. And we need to specify the status code so that we can tell what it is. We need to specify which API. Again, I'm doing this for this test project. Normally for your production code or for something that you write for the public, I wouldn't be using APIs because, you know, obviously you can use, you know, many more options here. Now for that, I would use, for production code, I would use one of my utilities. If you go into my website, utilities, and then look up seekIDGen and kind of read about it here, it basically generates unique values, unique code numbers, integers, that would let you provide here as a, you know, as a ID for that specific error. But for now, just for readability, I will use just the API name here for us. And what I would also use is a section type. Now this is important so that we can tell what type of section we actually saw an error in. Okay, and then we can reuse actually this format for any further errors that we encounter. Okay, so that will take care of the return value from our singleton API. But before we go, we need to initialize, we need to set up the first parameter. And the first parameter is this RtlRunOnce structure. It's kind of like opaque structure that the function uses to store all of its parameters. And we will use it here. Let's see, it's not a pointer. Section singleton state, okay, for the lack of a better name. So, and we can use it for our for our singleton. Now we need to provide a pointer to it, but before we can use it, we actually need to initialize it, and we initialize it here. Again, if we go into description, let's see, we need RtlInitialize routine. Let's just copy it, and here let's see, RTL, oh, I'm sorry, that's not it. Where is it? Well, I guess they did not put it in here. Here you go, that's the name at the bottom. So this is, you know what, let me just type it in. Basically, it's RtlRunOnceBeginInitialize, and this API will just initialize this structure here for the first time. And let's just say initialize our singleton. Okay, because without it, this parameter will contain some random gibberish, which would be bad. Okay, so we initialize it here, and then we get to our point here when we can use our singleton. Now, the thing that we need to do, we also need to finalize our singleton, because, you know, it's not, let's see, singleton, somehow I have a spelling problem today. Let's see, RtlRunOnceComplete. Now, to call it, we also need to provide a pointer to our state, and the flags are 0. And we need to provide our context. Now, we will fill in the context, but initially we will assume that it is null, which would mean there's an error. And right here, we also need to check a return status, which will be another value. And in case this is not a success, we need to process it. Right, so we check not NT success, which means that this completion of our singleton failed, and in that case it's an error. And you know what, let me add an assertion here so that it can actually stop and show us that there is a problem in our logic here, because technically these APIs should not fail, and they would fail only if we have the break in logic in our program. So as you can see, I'm reusing the calls here. I just changed the name of the API. It would also provide section type, and status will be status2. Okay, now, and then the reason I set the different status is so that we don't mar our previous status that we might be using above. And we need to check if we have status success for our usual status, then we actually override it. So it's kind of like a double thing here, you know, because we're getting the second variable, and if the original status that we return is success, then we need to set it to our failure here. Okay, so this will be our singleton, kind of like make sure that it actually compiles, and it does. Again, so the way this works, the first time the execution comes to this API, it will return status pending. So we will get to this chunk, and over here we will set up our, let's just quickly create our section. So we will create it here. We will store it, the pointer, to our section, or actually to this structure that will contain our section object plus additional stuff. And we will store the pointer to this object in a context. And then when we finalize our singleton with this call, we will store a context in it, and hopefully not fail. So the next time when this API calls, the second or any subsequent time, the API will return success and will also provide the context that we set up here in this call. So in other words, it will be called only once, and then we'll just get a pointer that we will return here. So this is kind of like the basic concept of our function. And the thing that we also need to do, we need to ensure that we can handle the situation if we did not get the pointer. So if we did not succeed with our context, and it might happen that the status is still success, because you know we get status from this API, and we would get success even if the context that we set originally was null, if we did not create the section. So in this case, this means that we previously failed to create section. In this case, we need to change the status to something else, and for the lack of better name, let's just pick some error code like non-existing sector. Now I know it doesn't make too much sense to use the word sector here, but what I'm going for is the word non-existent. So if we get this error, we will know that, hey, we did not create a section in a previous call. Okay, so at this point we need to actually go into creation of our section. Before we go into creation of our section though, I need to explain something. Now technically we can just go in and create a section as a, just load our DLL into memory and just create it this way. But there are some restrictions that may apply, and mainly Windows 10 introduced some security features that might prevent our section from loading. So if I run Process Hacker on my test system and run it as administrator, well, as an example, let's just start edge, the new edge. Let me just minimize it so we don't see all the stuff that it shows. If we look into some of the processes it creates, I'm not sure which one, not this one, let's try something else. They're all named similarly, so I'm just guessing. Okay, like this one. Now if you look at, again, if you go into general properties, general mitigation policies, and go into details, there's this property, this policy, mitigation policy, which is called signatures required, Microsoft only. If we go into, if you search by code integrity guard, you will find this blog post from Microsoft that basically explains what this mitigation policy is. In kind of like 2 words, this code integrity guard, or CIG, is a special mitigation policy implemented in Windows 10 that prevents loading of modules or DLLs into a process that are not signed by Microsoft. Now, what is this? Well, if you look at, well, let me just do real quickly. If we go into some file, well, like for instance, like one of my files here, which is not a DLL, but just to show you an example, if you go into properties, you would see that there is a digital signature, right? So this one basically says that I signed it. Well, this mitigation policy that says, signature restricted, Microsoft only, will look for digital signature on a DLL to be from Microsoft only. And if it's not, it would not load that DLL into the process, which is a very nice security feature. But it's a problem for us because we're trying to inject our DLL into all processes, including this one or the other ones. Like for instance, if you look into like antivirus for Microsoft, it also has similar restriction here. So that would be a problem for us if we just create any run-of-the-mill DLL and try to, inject it into processes like these. So we technically need to find ways to bypass this code integrity guard. And there's also this arbitrary code guard, which kind of like is a little bit different, but also kind of deals with the similar stuff. So again, read it here in this blog post. And they applied it to Microsoft Edge, but it's technically, it applies to other Microsoft products as well. So how do we bypass it? Well, one way to do it is to create what is known as KnownDlls. So if we go into WinObj, tool from sysinternal, and go into KnownDlls folder here, you would see a list of DLLs that Microsoft grouped. Those are kernel objects, which they call KnownDlls. It's kind of like a directory for kernel objects, where they combine all of these well-known System32 DLLs that they load without any security checks. Now, this is kind of a like, well, it serves several purposes. They created it some time ago. I believe it might have been Vista, but maybe even Windows XP. So the basic premise is that when DLL is loaded, well, it's a slow process because of the legacy requirements. The DLL, the loader had to look for DLL all over the drive, and then it had several folders to look in. Then it would have to map it. It would have to do, lots of other stuff. Additionally, now with all the mitigation policies and securities, Windows has to perform all those checks. And there are some DLLs which are coming from Windows and System32 folder, which are considered trusted. In other words, to change them, you have to have administrative access, and in that case, not everyone can have access to them. So by creating this kind of like virtual folder, or virtual, known DLL objects in kernel, the loader can bypass all those security restrictions if the DLL is in this directory. Well, we can also use it since we have a Windows driver, and if we add our DLL into this KnownDlls folder or directory, we can actually bypass all of those security checks. So, and that's what we will do. Okay, so let's go back to our coding environment, and let's do it here. Now, to be able to do this, to create our known, let's just write it down, known DLL section, we need to add a few things here. Now, first, we need to let's just say trick, not tick, but trick the system. Now I'm going to put very simplified comment here so that the developer that reads this would kind of like understand what I'm trying to do here. We'll need to trick the system into creating a known DLL section for us with the security descriptor of the kernel 32 DLL section. So I will explain what this is. We will basically take security descriptor from kernel DLL and apply it to our own section before we create it. And but to be able to do this, we need to temporarily attach ourselves to, let's say attach, not to, but the current thread to the address space of the system process. This is needed so that we can actually create a known DLL with this very high restrictive security descriptor. And for that, we use an API which is called stack attach process. It needs a process, P process reference. And let's see, and then it needs a state. So we will create our state here. KAPC state. Let's do it this way. And as a process, as a PE, we will use an internal initial system process. So this way we will attach to PE process structure of a system process. Then we quickly create our section, and then we need to revert back. We need to do it, you know, as quickly as we can. And let's do KE unstack detach process. I'm always struggling with the name, and we need to provide our APC state, and this way we will do quick attach and detach. Okay, and then we need to create a function that will create our section. But before we do that, we actually need to allocate memory for our structure that we will be creating, because again, the structure obviously takes some parameters, so we need to allocate it on the heap. I'm sorry, not on the heap, but from the pool, from the kernel pool. So we would do, let's call it, let's say dstats, and we will use allocate, let's see, allocate pool. Let's see, I have so many with tag. Here you go. So it takes 3 parameters. First, we will need pool type, and we will provide it at the end. Then we need size. Well, this one is easy. It's just the size of our structure here. And then we need to provide a tag. Now, again, we'll get back to it. Well, okay, now pool type. Now, to make it again, what I like doing, instead of coding it, hard coding it, I would like to provide all the allocation types inside a definition, inside the H file. And the reason I want to do that is because all of our allocations here would have to adhere to the same pool type. Because this API will be called from inside of our onload method, which is, let's see, where is it? We need to kind of like stick to the same pool type. Now, it is called from within a special critical section or a lock, and the RQL level can be also different, so we might have different restrictions on the type of the pool that we can use. So let's go back, and we'll play with it later, but let's go back here and define, let's see, allocation type on load image. And for now, let's just say paged pool. This is the most abundant one and kind of like recommended to be used, so let's stick with it so far. Let's add some space here, and we can also provide a reasoning. Well, let's just say if we go back into our description here, we can actually see the callback, and we can actually read it here and see that this is called at passive level, right? So our routine, our callback routine, or our onload is called at the passive level. So technically this would allow us to use paged pool, and let's provide it here, a little comment here. We can do it because, let's say, the OS calls the driver's image load notify routine at passive level. Okay, And if we learn that we can't use this logic, then all we have to do is just change it here instead of hunting for every single allocation and change it that way, which will be pretty error prone. So with this way, we just change it in one spot and just use this preprocessor definition pretty much for any allocation. Okay, so this is my way of doing things. And last thing, we need to provide a tag. Now, what is tag? Well, tag is just a 4-byte value that is used for, well, just debugging. If for some reason something fails and we get into a crash dump, the debugger will check if there is a tag, and if there is one, it will provide it for us. And this is just an easy way to see which memory area the error happened. So in this case, let's provide it. But before we do, I actually have a little helper macro that I usually use for this kind of purpose. So let's go back into driver type, and well, just for the lack of better placement, I'm just going to copy and paste it here. So what it does, it just basically flips. Well, let me just show real quick. So if we go into our location here and provide tag, and then in quotes, we can actually specify a string that we can use as a tag. Like, for instance, it would be KDSM. So what it does is just basically, it says kernel and GetSection, just kind of like little abbreviation here that would let us provide just a text here. And the reason I'm using this inversion here, or change of bytes, kind of like around the first byte goes to the third byte and the second byte goes to the first byte with this macro, is so that it's kind of like reversed. So in other words, if I didn't have this tag, let me just kind of like comment it, I would have to do something like this, kind of like write in reverse, which is not very easy, because then when you search, because it will come out as such in the debugger, and when you search for it in the project, well, guess what? It will find this, but it will not find reversed one. So that is why I wrote this little macro that will just flip it around. Okay? So that's my little tag here. And again, this is nice to provide it so that we can actually refer to it later if we have a problem. And over here, we don't have a cast, which we need to do. Okay, so at this point, we get our allocation. Now keep in mind that it may fail. So let's write it this way. And if it fails, we always need to we need to process this error. First, we need to provide our own status, because the API doesn't do it for us. And in this case, we would say status memory not allocated, so that will tell our program what the problem is. And then we need to put a little error message here. Obviously, I'm doing just copy and pasting here. And what I'm going to do, I'm going to put this API, and in quotes, and I'm sorry, in brackets, I'm going to put the tag so that we know which allocation failed. This is kind of like, my way of just doing some debugging output. This is very handy. I'm going to put error here. So in this case, we get our allocation, and we also need to check the condition when we fail to finalize our singleton. Also very important thing to do is to free our memory. And the way we do this is using x free pool, and we provide our pointer here, and I always null it out so that we can prevent situations when the pointer can be used after free. This is important. And in this case, we just, you know, nulled it out. And the other thing that we need to do, we also need to null out the context so that we don't return an existing value. Okay, so in this case, we got our value here. And then what we need to do, we need to call our function that will create a known DLL. Let's just say, you know, just say true. There'll be a function here. And then we need to, let's say, keep, let's say we'll keep the section info in the context, right? And the section info will go here. And by the way, let's do it not here, but over here. When we check the status, let's say check the result, and let's just say NT success, check status, and we'll keep it here. Otherwise, we'll say it's an error. And we will also free memory and provide a description. And the description will be our function name here and status. And just, you know, so that we can code it later, let's just call it create known DLL section, right? So we'll have to code this function, and what I'm doing, I'm trying to like minimize the calls inside this little area where we where we temporarily attaching itself to the system process. We need to pass a pointer to it. And basically, yeah, that's it. So we create a context. We'll work on it here. Then we will actually fill it in here. And if we fail, we need to say that create known DLL failed, and we provide the reason why. And if it fails, we also fail with the status. And if it doesn't fail, we set the pointer to our object here, and we'll fill it in again in this create known DLL section. And then the context is actually stored in our singleton. And then after that, when we call it next time, this function will return success, and we will get the context, which will be our allocation here. Okay, so at this point we have a full function here that will get us a singleton for our DL stats structure. Okay, so the next thing to do would be to actually code our function to create known section, and we can do this in the next installment of this tutorial. For now, I'm going to stop it just so that I don't make it too long. And for now, thank you very much for watching, and I will see you next time.